Hi, Jordan. How you doing? Are you excited?
Yes, it's nice to finally get a look inside the beast. We got that leak from electric like a little over a year ago before Battery Day, and this gives us a bit more detail because we were kind of looking at it from side on, those discs, and we didn't know if it was a plastic disc or metal, but now it looks like it's confirmed that it's metallic and it actually goes over the tabless flat.
And what is your sense? Like, what are you reading into this? Like, I've been seeing these pictures for a little longer than you have. You had about an hour and you upscaled them. If people want to look at you up on Twitter, you've upscaled them 2.5 times. But what's your first impressions? Like, what are you reading into this?
That's actually something I'd like to talk or walk through with you,
Hmm.
because I think you mentioned on Twitter that you thought it was something to do with shock, and that may be the case. But my first question be, if it was shock, um, why would shock be a problem with the 4680, but whereas it's not an issue with the 2170 battery cells? It very well could be shock, but to me, it seems like it's something more to do with connectivity. Once you compress those, the compress it into the can and you put the lid on, you need a way to maintain connectivity. And when I looked through the patent, there was about a dozen different ways that they were thinking of doing the connectivity, but this is different from anything that was in the patent.
Okay, so let me start by saying if you research a little bit about 21, well, lithium ion cells and vibration, there's a whole series of tests that are standard for the industry. And vibration and shock is a big part of those tests. And there is some damage that can occur, especially in cylindrical cells. You'll find that they can like damage like the the cathode and the anode like jelly roll. So if there's shocks or vibration, long-term vibration, damage could occur. And you know what happens when damage occurs? It could be problematic. Second thing is what I'm seeing in what I saw in this is like if you look at the assembly, like the manufacturing, if you look at the can itself, you'll see like I'll call the cathode on top the nipple, for lack of a better word. And I'm thinking that they go through the jelly roll and basically weld that centerpiece of the cathode current collector to the inside nipple. And then basically, if you put it vertically, the spring-like things extend and they go down a bit. And then they weld those 6 tabs of the anode current collector in a specific place in the can. So basically, it's like between like shock absorbers, between like two springs. So basically, the whole thing can be free floating in there, and the shocks won't it won't hit on any of the surfaces because going upwards, if the G's are too strong, it'll be retained by the anode, and if going down, the G's are too strong, it'll be retained by the cathode. So this is where I'm thinking that the thing is in like almost like in suspension in the can. This is where my mind was going when I saw this. I don't know if you're reading the same thing into this.
I definitely see what you're saying. It's a thought that passed through my head. Basically, you're giving each battery cell kind of an internal suspension system to protect it from shocks and vibrations. But I guess if the 2170 doesn't have an issue with that, it's a solved problem there. Otherwise, they wouldn't be putting them in vehicles. Why would the 4680 be having issues with mechanical vibration damage issues, whereas the 2170 did?
Well, it is a heavier jelly roll, so it will be more susceptible to high G forces. To basically like the momentum that it would carry with it would probably be stronger than a small 18650 or 2170. Like I said, there are actual tests that are being done, and one I can share with you maybe the paper I was reading. They basically said that cylindrical cells would pass the test, but when they analyzed them like through X-rays, they saw a little bit of damage, but they still passed the test. Like I think it's UN don't remember exactly. There's a whole like standard of testing. I could find it again. And so it's basically like
Yes.
if it's heavier, you might need those shock absorbers. And it's also an extra safety feature where you're sure that because a lot of people thought that the bottom, like the copper flags were like in direct contact with the bottom of the cell. Of the cell can, and that would be the ideal place to like remove heat. Whereas now we can clearly see that the heat that's being generated inside the jelly roll is basically going to the copper flags, which are connected to this copper cathode anode current collector, and being welded on like 6 large surfaces inside the can, but on the inside wall of the can. So this is where the heat is going. It's on the bottom portion of the inside wall of the can, not the bottom at all. I don't think it even touches the bottom of the can.
Yeah, well, going back to the vibration thing, if you, in order for that vibration dampening effect to work, uh, I would assume that the jelly roll would have to be able to slide like a piston up and down within that battery cell in order to take advantage of that shock effect. Whereas generally, these battery cells are so tightly packed in there that they don't budge at all. It's as soon as they put that electrolyte in, it's just jammed and it can't move. So um, I wouldn't I wouldn't see that you'd be able to take advantage of that spring effect unless the jelly roll can move within that can. But we might be getting into too much detail here. I
No,
don't
no,
know.
no. Like fair warning to everybody, we're nerding out on like engineering and manufacturing of these cells. So yeah, this is what it's about. So yeah, let's deep dive into it. Yeah, I would agree with you. Like when you look at people like taking them apart, it's usually a pretty tight fit. I don't know how slippery though that outside white covering is, and how much.
It's made of the same stuff that plastic bags are made of that you get at the supermarket.
So it's actually very slippery by nature.
Mm, yeah. But it is like if you have you ever tried to pack away a sleeping bag after you've gotten it out of its original packaging? And it's like that's how
Yes.
tightly packed the stuff is into that battery cell can. So you can't in order to get you can't just pull it out no matter how hard you pull. You actually have to peel it out like an
Mhm.
orange peel.
But do we agree that if they wanted had to make it rigid, like both the connection to the cathode and the anode to the can, they could have made it rigid. There was nothing like preventing them from like not having these cut out like leaflets that look like springs. This is an added step. It
Well,
has to serve some purpose.
yeah, when I look at them, it looks like they're cut out in a way that if you, I can't think of a better example, but you know how there's a condom, like you have the edges of the condom, and then you kind of roll it over whatever you're rolling it over. It looks like it's something, it looks like it's something like that. Whereas as you compress the lead over the top of it, I think some of it will fold down over the sides, and the things that are sticking up will compress flat.
No, this is where I disagree. First of all, because there's like
Okay.
6 gaps.
Yeah.
So you would have places where you like the crimping would be leaky basically because it would try to crimp. So all these 6 tabs on the anode side, the copper side, maybe I'll just start saying copper. Everybody should know that the copper side is the anode and the aluminum is the cathode. So we might simplify. So the copper, those 6 copper tabs are actually welded inside the can, and the cap goes over it, but it does not crimp over these tabs. And you can see like on the
Yeah.
aluminum
Well,
side, it's basically the reverse. Like those leaflets, the springs, because it's connecting to the nipple, are all pointing like towards the center instead of the outside.
yeah. Well, here's one thing I thought when I saw that image. What aren't we seeing? Because I bet you there's technology inside the cell can and on the thing that's crimped that the interface. So I guess what we're missing is the interface. So we're kind of taking stabs in the dark, but I do feel like we're getting somewhere. Now, I, I I don't. My view is it would still be that it serves the purpose of electrical connectivity rather than some sort of vibration dampening effect. Um,
Oh, let's be clear. Like the first
yeah,
purpose of this is
yeah,
electrical conductivity. If you need to
yeah,
connect the jelly roll to the can in some way. But
yeah.
again, why would they cut these leaflets uh, if
I don't know because go
because
ahead.
these leaflets for they allow movement. Like if you would hold that current collector in your hand and you would flick it with your finger, it would move. And they didn't have to make it that way. They could have made it simply like a whole rigid disc to connect all the flags and basically like weld it to the top or to the bottom. Those are extra steps they took both on the aluminum side and the copper side to cut out and if you look at the copper side, it's even like pre-tensioned, like they've been bent upwards. And you know what happens with copper once you start bending it, you work hard in it. So it's basically it starts to become like a spring rather than like malleable. So like I said, I don't have insights whether it is or it's not. I just want to I'm not trying to convince you. We're working through it because I don't have that information. Neither does this Jordan. Yeah.
Oh
So
yeah, I'm taking it in that um, with that frame of mind. I certainly don't have the answers, and it's good to hear your perspective because as I'm looking at it now, it's if it did kind of peel or stretch over the top of that, the circumference would have to stretch as well. So
yeah.
I think my initial guess that it was some sort of stretch wouldn't work because um, there's there's no places in there where I can see where it would stretch. So it definitely has to be. Um, I don't think those are going to fold down and it's going to lay flat. I think you are right that it's going to kind of maintain that shape within the battery cell. So very well could be something to do with shock.
Yes, and if you look
Um,
at the aluminum is not like pre-stretched. Like it's pretty much laying down flat. You can see like on the angle photo that it's a bit like detached, but nothing like the copper side, which is like
mm,
maybe a millimeter or two, like already bent. And this is where I'm thinking because the cans are sitting upright, so the cathode nipple is facing up, that the weight of the jelly roll basically does the first extending of the aluminum tabs, the little flaps that they were cut. And the copper side basically is already pre-stretched to counterbalance that and be welded at exactly the right position within the can. So they're both sharing basically the load. One in tension, the other one in compression, if that makes sense.
yeah, it does make sense.
Hey,
So
Omar.
I think you're closer to the answer than I am. Go ahead. You can ask more something.
Yeah, how you doing, Omar?
Uh, I'm driving to San Francisco, so my audio probably won't be that great, but I came in to listen for sure.
Yeah, cool. Okay. Jordan, like other details, what are you seeing in these images? If we move away from these little flaps, how are like people were asking in the tweets, like how is it connected? Like what are your thoughts?
Well, this is what I'm missing from like we need to take a look at the cell can, but I think you're on the right track because if I guess panning back here for a second, you have the cell can, which is one connector for the battery cell, and then you have
Mm-hmm.
the nipple, which is the other connector, the positive and the negative. I don't know of any other way that they would be able to do this because it looks like there's a continuous connection for the entire battery cell. So I think that's one connector, and the nipple is the other one. So if both of these are massive, or yeah, if both of these are massive sheets of metal on the top and the bottom, there has to be something that isolates one of these from the battery and allows a very narrow connection to that nipple at the top, which would be the aluminum side. So
Yeah.
yeah, then there must be some type of electrical insulator at the top inside the can.
Yes, this is maybe another discussion to have some other day with different photos. But I'm
Yeah.
thinking if you look at people were saying how are these current collector attached to the flags on both sides? Do you have a guess as to that?
Well, I think you were, I couldn't explain it better than you did, which is that somehow those flanges are
No, no, no,
welded.
not the. Hold on, not the flanges. I'm talking about the flags. So what's underneath the collector?
Oh, okay. I think it's just, does it actually need to be welded? That's a good question.
Well, how would it remain in place if it's not connected to
Well,
the flags like in a certain way? Those collectors wouldn't stay put.
mhm. Yeah. Well, there's in the patent, the way they had it, they were going to use some sort of ultrasonic welding, a combination of ultrasonic welding and the shape of the top and the bottom of the can itself was supposed to maintain that conductivity. But I think their default was they wanted to be able to do it without welding, so long as they had the right shape of material on the top and bottom. And so you compress that in there, you jam it in, and that's what maintains the conductivity. And that,
Okay, so I might be able to like guide you a little bit. If you look at the photo you upscaled, especially like the first one, the copper, do you see that in between
yeah,
each like little spring, there's like three large lines and two short lines? What do you make of those?
yes. I was lost on that. To me, I see those holes must serve some purpose, but I don't know what purpose they serve. And maybe you with your engineering background have an idea.
Well, yes, they're not actual holes. If you really look closely, they're laser welds. This is how the current collectors are basically welded to the flags.
Oh, so what we're seeing isn't actually a cut through, that what we're seeing is kind of a bit of charring?
Yes, well, the metal that has been melted by a laser, that's actually welding the current collector to the underneath where the flags are. So like that rosetta of laid down flags is basically welded to that current
Hmm.
collector on both sides, actually, both aluminum and copper. And they both have the exact same pattern of welding.
Okay. And what uh, are you just, what gives you that indication? Can you just tell by looking at it, or is there, I guess I'm looking for the visual cues. Because to me, it kind of looks like we're looking through it into the metal tabs, but that could be a trick of the eye.
Yeah, it's a bit of a trick of the eye because if you, again, your first photo that you upscaled, and thank you for doing that, you'll see that on around, I don't know, like 10 o'clock, if we can call it like the 10 o'clock spring, if you look underneath, you can actually see the flags all laid down. But if you look at
Hmm.
those five lines, you don't actually see through them. There's like little like there's relief, so there's dark spots, light spots, but you're not seeing the flags through there. This is where the collector is basically pressed against the flags, and then a laser goes there and basically does all those 30 weld lines basically all around this in all the six gaps, five welds per gap, and this is what holds the collector firmly against the flags on both sides. So basically, once all that's welded, like nothing is coming apart. Because if it wasn't fixed to the flags, then that current collector would, it could
Got it.
short circuit, it could like bounce around and spark because it wouldn't touch like uniformly. But with these 30 welds, you can actually see that it's a firm connection for both electricity and heat, because that's also very important to being able to draw the heat to a specific area on the can.
Nice. Yeah, I wouldn't have picked that up. Yeah, I was stumped on that. Interesting.
Yes, and the thing that amazes me is that any kind of like impurity in a jelly roll can cause big problems. And they're actually, once the jelly roll is complete, they're actually doing welding on both sides, both to attach the current collectors, but then also afterwards to attach the aluminum current collector to the nipple and the copper current collector to the side of the can. So they have some pretty amazing technology to be able to do that and not contaminate the jelly roll.
Well, I think yeah, absolutely. And this is one thing I noticed from all the images that we saw and looking at the design of the 4680. And Panasonic raised the fact that this takes an order higher of precision than normal battery manufacturing, which in and of itself requires an extraordinary amount of precision. So for Tesla to be able to hit this kind of precision with the first battery cells that they've ever produced is pretty mind-blowing. They're doing more advanced work than any other battery manufacturer in the world. And this isn't something you can just do easily. It's really hard. So there's
go ahead.
Yeah, this with the welding, and then the narrow margins that they have around there's a narrow strip of metal between the current collector foil and the active material. I don't know how they're able to crimp that without disturbing the active material that's right beside it. I don't know if that makes sense.
You mean like when they cut the flags and bend them towards the inside, right? To do like the Rosetta of flags.
Exactly.
Yeah.
Yeah.
Oh yeah,
because if anything connects there, then you have a short. And that would be really easy to do when you're bending all that material at the top and bottom of the cell.
Yes, yeah, absolutely.
Anyhow, we're getting a bit off topic here. Sorry.
No. It's all about like nerding out on this engineering. Yeah, I got to say I'm pretty impressed also with the way they thought it through, of being able to, because there's probably no other way of welding the aluminum side. Like the copper side, it's on the open end of the can, so basically you have full access. I'm not saying it's easy, especially because there's a jelly roll that you could contaminate. But it's much easier than to weld the cathode side, the aluminum side, onto the nipple. But going through, that's the only way I'm seeing they could do it, is like going through the jelly roll, that hole in the middle, and basically reaching all the way to the other end of the jelly roll and basically tacking it either with laser welding or ultrasonic welding to the inside of the nipple in the can. And then afterwards, once that's done, then they weld the cathode side, the anode side, the copper side, to the inside of the can. And then afterwards, they put the cap on, they crimp it, and then they fill it with electrolyte. I think when you think first principles and everything, I don't see how you could do a better job than designing a cell that is assembled that way compared to how other cells, if you look how 2170s and 18650s are made, it's much, much more complicated manufacturing wise. Like when you put the cap on, they have to weld the tab and close it up and put the electrolyte before closing. And it could induce a lot of like rejects and poor yield, because you're leaving a big manufacturing step like to the end of making sure you have a sealed can. Whereas this, they basically do the whole thing before they fill it with electrolyte and start testing it and charging it for the first time and the maturation and everything. So I think there's a lot of manufacturing genius, but like design based. Like they designed this cell to be able to be manufactured, even though it's a complex cell to manufacture. They simplified it so much. And of course, they had to, like I said, the welding. I'm pretty impressed that they are able to weld the current collectors without contaminating. And the only thing that's possible to do this with is laser welding. No other form of welding will. Because you can't apply too much pressure like for ultrasonic welding. So the only thing that could work is laser welding.
Yeah, and for perspective for people, basically what we're looking at here, right underneath that aluminum top, the material below that is only 10 microns thick of copper. 10 microns is about the diameter of, what would it be, a red blood cell. So if you go deeper than the depth of that red blood cell, then you're messing up the material below and you might get a reject. So that's the tolerances we're talking here. We're talking cellular level precision. So, yeah.
And going at ultra high speed, it's not like they're building these like they're building Swiss watches with one guy like carefully under a microscope, like doing all these operation. This is like an assembly line. These things are shooting out like a machine gun. So yeah, on that side, I would agree with you. It's very impressive.
Hmm. Oh, and one thing, just as a side note, one thing I noticed when I was reviewing that footage from the advertisement for Battery Day, if you slow it down, you can see when they're winding the roll, there's a tear in the roll that gets rolled up into the jelly roll. So that was, I think, maybe you've mentioned in the past, but I've seen it elsewhere where they might have issues with tearing that super thin material. But it's, yeah, if you slow down the footage, you can actually see a big chunk that's torn off. Um, so, but it
Yeah,
sounds like that.
I haven't spotted that, but I'll keep a lookout because I went frame by frame to find like the bottom of the cell, and there's actually only one frame, and it's my pinned tweet, and it's total conjecture, like what it is about, like the closing of the hole and being a safety vent. But yeah, I went frame by frame, and I didn't pay attention to the. I think I was skipping over it because I was so focused on finding a perfect image of the bottom of the can instead of like the jelly roll. But yeah, like going at those speeds, winding speeds with material, like you said, that is so thin, you're bound to have some tears, and you need to adjust like the tension and the speed and everything, so that doesn't happen.
Yeah, it's super delicate and totally understandable. There's, I didn't even notice the thing you noticed about the top of the cell can because you really, in order to catch this stuff, you have to go through it frame by frame. The tear that I'm talking about, that's also, I think, maybe one or two frames, and it's blurry, so it's hard to see. But there was, yeah, you can spend hours tearing apart that footage and pick out details.
Yes, and I'm thinking they almost probably did it a little bit on purpose because they could choose what they show and don't show, and leaving
Yeah.
like one frame, a clear shot of something, might be just done on purpose. We don't know. That's conspiracy theories. But let me ask you this: like, what else are you curious about the 4680 manufacturing or the design of the can? Like you mentioned, like the nipple, how they insulate basically the cell body, the can, from the nipple, which is the cathode side. Is there anything else that you're mystified about or unsure of?
Yeah, I feel like the only missing piece that we have now is what the inside of that can and the lid looks like. And oh, and how it deals with thermal runaway events and how it deals with shorted cells. One thing I noticed when I was looking at the Giga Berlin images was generally the separator is super thin. It's yeah, like less than hair thickness. And around the outside separator, it looked like there was a thicker piece of material. I'm wondering if they put fire retardant material inside the battery cell as well around the jacket. Because I think one of the key concerns with high nickel battery cells is the fact that they're flammable. I think one of the probably the design parameters that Tesla had for this battery pack was we want to make sure that this thing uh, isolates thermal propagation as much as possible so the entire vehicle doesn't catch on fire. Like for instance, maybe you have one battery cell go, it punches through the top, blows out the bottom, but it doesn't spread to the rest of the pack. If you can get that level of safety with these high nickel battery cells, um, it provide for me as an investor, it would provide a lot of reassurance.
Oh, absolutely. I know nothing about the inside of the can. My theory is basically like they're stamping like the can body as they stamp any type of sheet metal. So basically like cutting out discs and then like deep drawing them on forms, on presses. And I'm thinking the nipple is basically there has to be some insulating material that covers the whole top of the can from the inside with a little hole. And I'm thinking the nipple could be like some sort of rivet where they're basically like a large flat bottom that's on the inside of the can and a thin bar that sticks out. And then they basically press it and compress it so it makes a tight seal. And that would be how I think I would manufacture it to like reduce cost. So basically, like I think swaging it is the term in English, where you mold metal like by pressure and maybe also spinning like a rivet, and just basically like crunching it down. So that rivet would actually pinch the insulating material, which is the white thing that we see protruding at the top around the nipple, that looks like a white plastic material. And but that little disc outside would be huge inside, so basically covering the whole inside of the can at the top part, so you couldn't have a short on that end. That's my theory. I don't know if that makes sense.
Yeah, that aligns with what I'm thinking. I noticed that white gasket around the nipple as well. And I assumed it was insulation material so you could isolate the connection with the aluminum current collector. But I was like, okay, well, how do they do that on the inside then? But what you're saying makes sense to me. It's as good as a guess as I could muster, at least.
Yeah, it's because it has to be also very cheap, like manufacturing wise. You can't have a super complicated can, or else like the cost benefits aren't going to be there. So that's the only way I could. Well, and I'm not like a manufacturing expert by any stretch of the imagination, but this is what I'm thinking: like simple manufacturing methods that are used elsewhere could be used there. For the whole like safety part, I don't know if there's anything in the can. Of course, everything is basic safety. Like if this is a shock absorber, it prevents some damage from vibration and shocks. But I think for like thermal runaway, I think the whole bottom, and we might do an episode eventually about that, about how the structural pack will be assembled and what it looks like. But I think like the whole bottom structure, I think I was replying to somebody on Twitter, you have three sides to these cells. You have the top, the bottom, and the can itself, like the surface of the can, the cylindrical cell. And it's very hard to combine two functional aspects on one surface. So you need to connect these batteries somehow, and this is the top, because you have both anode and cathode available on the top of the cell. So what makes sense is that. Then the sides, and we've seen them in leaked photos, and we've seen it at Berlin, the sides are mainly used for cooling. And then you're left with the bottom, and the only last aspect that you have left is actually like the safety aspect for thermal runaway, but also for shock. If something comes up from the road, like you roll over something and it punctures your pack, you don't want it to be in direct contact immediately with a cell. You probably want to have a gap, a safety gap, where you can manage some perforation of the pack without ever damaging a cell. And I think it works the other way around too. If something happens within a cell and it starts to go into a thermal runaway, then you would have, cooling is the number one thing to keep it from going there. But if the cooling, because the damage is too severe, is not managing that thermal runaway event, well, then you want somewhere where you can like purge all this hot material in a safe space that will not come back and bite you in the ass on the other cells that are adjacent, and then do a cascading effect, which could be disastrous.
Yeah, it's so that's an open question mark for me as well, because in basically the 2170 battery cell, there was a lot of safety built into that battery cell because it was going to be used in laptops. Whereas with the 4680, they can afford to, I think, strip some of that out, and monitor and control these battery cells electronically. And then if there is an issue, have some sort of exit route for ejecta, discharge.
Yeah, well, maybe you can like tell our audience what are those features that were in the 18650s and 2170s, those safety features that were mainly designed for laptop batteries.
Oh, I think some of them actually contain a chip at the top, but there's also there's like a diaphragm, and that diaphragm ruptures, and when the diaphragm ruptured, it also severs the electrical connection. So basically,
yeah.
the cell isolates itself from the rest of the battery cells. And then on top of that,
and it also had air vents, right? Like three little microscopic air vents that once you punctured the membrane, it could actually discharge hot gases outside without the cell like blowing up like a balloon.
Correct. Yeah. So it gave it an exit path, but Tesla may be able to do better than that in a more simple way, given that they're designing battery cells to be part of a larger automotive pack rather than single use, or 3 or 4 in a laptop. So it's basically we're still using battery cells that were meant for laptops, and Tesla has an opportunity here to redesign them for a vehicle use case.
Interesting. We could take questions also from the audience if people have questions, comments, or they notice something in these photos or like their own knowledge. Like, feel free to call in and give your opinion on this. Here we go. So we have Ken. Welcome, Ken.
Hey there. Hi, guys.
Yes, go ahead.
Yeah, I attached some photos that Gally took to limiting factors tweet.
Mm-hmm.
And if I was wondering, I saw the picture. This is the last one I put. My name is Kenneth K. If you look at the last picture, it shows the electrical connections, right? So
Yes.
If you look at that, you do see the white ring that must be the isolator between the anode and cathode.
Yeah, well, that's the outside of the jelly roll. So basically, when they finish rolling it, it's a white plastic bag material, as Jordan was mentioning, and you can actually, I think, even make out a little bit of that blue tape, which is holding the whole thing together, so it doesn't unwind.
You know what I'm talking about? At the Gigafactory Berlin, they had some videos.
Mm-hmm.
I mean, some pictures.
Yes.
So if you look at the pictures I attached to the limiting factors thing, you see the electrical connections that are be done at the top of the battery cell.
Okay, so you gotta your last photo, which is like basically a cell that's opened up. Right.
Refresh one more time.
Oh, okay. Hold on.
It's after that one.
Okay, yes. Those are like the current collectors for the whole pack level. So this is where you connect these cells in series and parallel to create the right amperage and the right voltage.
So you can see that white line, a white ring around that, which must be the isolator.
Yes, absolutely. This is what we're talking about. But the question is, what does it look like inside the can? Because you also need to insulate. Mm-hmm. Like if you imagine the jelly roll coming out through the bottom, the cathode is basically cannot touch the can. It can only touch the nipple. If it touches the can, you have a short circuit.
Right. So there must be some insulation someplace else that we don't actually see, right? So
yes, absolutely. Absolutely.
And in the other pictures that Jordan attached, so you see the copper with the hole in the center, right?
Mm-hmm.
And those rings around the outside, that must go in, attached to the can, and then on the top, this must be the top of the can, right? With the center that we see on the lid.
No, hold on. Like your previous one with the can opened up, that's the bottom. That's what we call the bottom.
Oh, okay. Oh, that's the previous one that I had. Okay, that's the bottom. Okay.
Okay, you can see actually the copper flags of the tabless technology. Yep. That's the bottom of the can, and that's where they close the can up. It's by the bottom. The nipple on top, that's the cathode, and this is what at least I commonly call the top of the cell, because they'll be mounted like vertically with the nipple pointing up. So what you're looking at on the other one, where the can is like slightly open and you see the jelly roll a little bit sticking out of it, that's the bottom of the can.
That's the bottom. Okay. Now on the top where the electrical connections are made, then that is where we see the copper looking thing in Jordan's picture, right?
No, that's the aluminum side.
That's the aluminum side.
Yes, the aluminum side is the cathode, and it's basically connected, just the center part. Like if you look at the photos, the aluminum side is also like cut as an hexagon. So there's 6 little strips but they're connected on the periphery of the cell, and they're loose in the center. And this is where the center part of the aluminum current collector is welded to the inside of the nipple. And that's the top of the can. And then the bottom of the can, you have the copper current collector that's on the copper flags, the anode side, which is welded to the side walls of the can.
Oh, I thought it was the opposite way around, because you see the aluminum that's connected in the center, whereas the copper is not connected in the center. So something like pushes out through there. I thought, but I guess not.
Oh yeah, that's the thing. The photo you're seeing at Giga Berlin of the can with the copper, like where you see the inside of the jelly roll, the current collector is not on that photo. And the most logical reason is Tesla is most proud that their largest innovation in this cell is the tabless technology, where like the whole foil is basically creates, and these are called flags. So all these flags are basically cut and folded down. But if you put the current collector on top of it, you don't see the flags anymore.
Now, do we have flags on both sides
Yes.
of the jelly roll?
Yes.
Okay.
One side, it's aluminum flags that are all laid down in the exact same way. And on the flip side, it's copper flags, which are all laid down in a Rosetta pattern.
Right, and that's where you think that's laser welded some way to those
Yes.
copper or the aluminum.
Yeah, once the flags are all flat or almost flat, they basically weld on each side a current collector.
Yep.
One is aluminum and one is copper. The one is aluminum is basically welded straight in the center to the nipple of the battery, and the copper side is welded on the periphery of the can. And that's why both current collectors look so different, because one has like flaps, 6 flaps going all around it. That's the copper side, because it's welding to the outside of the can. And the aluminum side, which is the cathode, is basically loose in the middle, only in the middle, to basically weld just on that nipple.
Okay. You think that these could be pushed in the can in those little, you're saying how the copper is preformed, it's like a spring. Could that be to make up any error in the length of the cell so it can compress?
Well, we started that discussion in the beginning. I don't know if you were there. My theory is that it could be a type of shock absorber. So so basically, like if the cell is mounted vertically, like we see it in the structural pack. So basically, like the whole jelly roll is basically hanging by the nipple where it's welded in the center of the aluminum current collector, and basically, so that's in tension. So it's like it's falling with gravity. And what's counterbalancing that force of tension on the top is something in compression, is those 6 little springs on the copper side. And basically the whole jelly roll has a little bit of motion available to it for vibration and shock without at any time bottoming out or bottoming up and banging into. So because you don't want to bang anything into the jelly roll, it's a fragile thing, and if you can have it like a little bit of play, but like Jordan said, these things are, once you put the electrolyte, like they swell and they're pretty tight in there. So my theory might be completely wrong, but for now, like they've added a lot of complexities to these current collectors. And the only reason I can see it's basically for some sort of mechanical action, or else there would have been like better ways you could have made it just rigid and, be one part of the can without any possible movement between the jelly roll and the can. Whatever the can does, the jelly roll follows along with it. So,
okay.
Alex, I think I just thought of a way to square your point of view with my point of view, which is you can still have that thing. It doesn't necessarily need to act like a spring. Simply by adding a little bit of distance between the current collectors and the top and bottom of the can, that will provide mechanical protection, because you won't have those two things constantly rubbing against each other during vibration. So it doesn't necessarily have to act as a spring. Just adding that extra space between the top and the bottom would provide mechanical protection. just
It's
from
true.
rubbing and friction.
It's true.
Yeah.
So basically the top, because of gravity, it's basically always like hanging a little bit. And so it's offset. And on the bottom, you weld it. So it's also offset. Yeah. Yeah. Good point. Yeah. I buy that. Does that answer your questions, Ken?
Yeah, thanks.
All right. Taking the next caller. Me. You're up. Oh, maybe not. So David, you're up.
He's
Oh,
on the
sorry.
stage.
Oh, I clicked the wrong thing. That's my bad. Well, go ahead, me. You're on stage. Okay, so putting it back into the audience. Okay, so people, sorry, this is my bad. Okay, so if anybody have any other questions, comments. Okay, so we have me who's back. Let me try it. There we go. Me, you're up. Just unmute your mic. Me, you're up. You can unmute your mic. It's the one right next to the little emoji on your bottom tray. There you go.
Okay, can you guys hear me now?
Yes, we can.
Okay, thanks, guys. So my question was around the heat dissipation. So we're hearing that the shell or the can is going to be made up of stainless steel, and if the copper foil is going to be welded at the bottom of the shell, and if we are going to have side cooling, like we were seeing in the pictures from Giga Berlin, and because stainless steel is not a good conductor of heat, how would side cooling work? I mean, is that going to be in addition to the bottom cooling?
Jordan, you want to address this one?
Oh, I think there's a lot of debate and open questions on this one because I think what they showed us at Berlin, I think it was missing a few, either it was an older version or it was missing, they might have left out a few details that are kind of trade secret. It was definitely an incomplete pack, but I don't know if it was on top of that, if it was like a prior version or something like that. But I'm thinking there's some way that they're getting heat from the top and or the bottom of the battery cell because that's the quickest path to get heat out of the battery cell. They're like thermal superhighways, that copper and aluminum that run through the battery cell. So those cooling loops come right down to the bottom of the battery cells. And even if it's just side cooling, I think there's enough conductivity there that it might be able to wick heat away from the top and the bottom. I think James Dalma was going to do some analysis on this. He was going to model it. But if he doesn't, I'd like to find somebody else that can do it. Because I think if they have all that copper at the top or metal at the top and the bottom, and they aren't taking advantage of it, it'd be kind of silly not to take advantage of it.
Does that answer your question, me?
Yeah. Another question I had was,
yeah, go ahead.
So would this cell design work for LFP as well? Would Tesla?
That's a good question. I've been running the numbers on this one a little bit, and the main reason why they use prismatic battery cells for LFP is because LFP doesn't have very good volumetric energy density. Usually people are focused on watt hours per kilogram, but with LFP, the volumetric energy density is so low that they have to pack those battery cells into squares in order to fit that much energy under the vehicle. Now, with Tesla's structural battery pack and their ability to tightly pack these cylindrical cells so closely together, it looks like, at least based on the numbers I've run, they should be able to get at least a 54 kilowatt hour battery pack using the structural battery pack. So to me, it makes more sense for them to use the 4680 rather than to add another form factor. And if they want to increase the energy density further from there, the best way to do that would be through the chemistry by potentially adding some silicon. And I think in the short medium term, they should be able to get up to 300 watt hours per, get up to 300 miles of range. I think they should be able to at least match what they're getting from their battery packs from CATL in China, and then over time increase that, getting closer to 300 miles. And in the really long term, they might actually be able to get a long range battery pack with LFP, but that would be 2025 and beyond.
So you think there would be 4680s with LFP chemistry?
Yes.
Okay, cool. Thanks for answering my questions, guys.
Good.
Thanks a lot, me. Going with David next. You're up, David.
Okay. Hi there. I was just going to continue down the thought process on the thermal side of things that was brought up. So, Alex, I think you mentioned, which I think Jordan didn't notice at the beginning, I didn't, that there's laser welds on the copper tap that we're talking about down to the tablets or the tabs of the
just like
design, right?
Yeah, nomenclature. Hold on, just nomenclature-wise, because it's tabless technologies. Yeah. Those things are called flags.
Right. Okay, flags. So we've got laser welding. You've got those 5 laser welds each section. 3, it looks like 3 long ones and 2 short ones. And then those correspond with the tab that then is welded and conducts into the can. Correct?
Yes, that's like how it is like binded to the flags, but all this thing is like compressed. So all the flags are basically touching the current collector, both on the copper side and the aluminum side. But yes, like they're fixed with those.
Hence we get the presumed thermal benefits of this tablet. But then as far as the flow from there into the can, I mean, we're looking based on this design, it looks to me as if the flow is going to be going into the sort of corner edge, predominantly at 6 points. And then there's obviously going to be some that's making its way through these other contact points.
I'm not sure I follow you. If you look on the copper sides, like most of the circumference of the current collector, because it's like split like most of the circumference, it will be in contact with a can. There's little gaps between the 6 flaps.
Right.
But like most of it.
The prime contact is on the circumference as opposed to.
Yes, exactly.
You know, I think like Jordan, when I first saw the flags of the tabless design, I sort of imagined a plate flat across all of those that then also would be flat to the bottom of the can, and thereby, you know, the prime heat flow would be straight out the bottom as opposed to around the circumference and thereby sort of more proximal to the walls.
Yes.
Hence,
I think there's 2 reasons to this. One is Jordan mentioned it, is basically it could be like a protection, so it's not in contact neither on the top or the bottom, so it can't bang into it, so it can't damage it. And I think another part is maybe the one I mentioned, that it might be, you know, you need 3 functions. You need to like one side needs to be able to collect the current, one side you need to be able to cool it, and one side you need it for safety. And since you only have 3 sides to the batteries, one side and the bottom makes the most sense to be the safety side. So basically no current collection and no cooling. So it might be an intersection of properties, like to make the cell safer, that it actually connected to the sides, because like the coolant, you have more surface area to cool the battery on the sides than you do at the bottom, like the surface area of the bottom disc. And if you look at it, the geometry is not exactly the same, because if you look at the video from Battery Day or like my pinned tweet, you'll see that it's not as the corners aren't as sharp as the one shown in the blow up on the big poster at Berlin. You see it's much more rounded, and in the center you have also a little nipple with the dark spot. So there's a lot more geometry. So you would need, if you wanted to pull heat out of that geometry, you need to have something that matches that geometry exactly to be in physical contact with it to basically pull heat out of it. Whereas the side of the cell is perfectly smooth, and you can have something like a ribbon just basically hugging it and like drawing the heat from there.
Right. And Tesla's already got a lot of data on that, over that design approach. Jordan might be able to answer this, which is on the thermal side. Is there, I mean, I assume the heat distributes through everything, but is there the most of the heat's coming from resistance of the movement of these ions that are shuttling back and forth? Does that concentrate more on the anode side as it's trying to get out of the anode and, you know, at the time of discharge and move, or is it pretty even, you know, and unimportant as to whether you're pulling from cathode or anode side?
That's a really good question. I haven't looked into that specific question specifically. My assumption was always that because these layers are about as they're about 50 microns, give or take, so they're about as thick as a human hair. So the thermal propagation with materials that thick, I don't think it would matter. But I am curious to see some sort of thermal analysis of this to see if you could actually wick the heat away from the side. Because my one concern, if you do try to use ribbon cooling on just the sides and not plate cooling, is there would be a gradient. There would be a heat gradient, and therefore you'd have a degradation gradient, because the degradation of a battery is linked to the temperatures that it hits. So it looks like they're doing the ribbon every other row. And once again, we don't know if this is the final battery pack, but if it's every other row, you'd have the far side of the battery cell that may not be getting cooled as well as the near side. So I'm not convinced yet that they can do away with plate cooling. Maybe Alex has contacts that have information to the otherwise. I'm just working based on what we saw in Berlin. But yeah, I'll leave it there.
Yeah. And one last thought on just the plate cooling was Alex was talking about protection from ingress from below from anything on the road. And I always thought that the plate cooling might offer some of that protection area, you know, because you have a void, an area with a void there. So.
Well, yeah, on top of that, you also need for to create that honeycomb, I would assume you'd need some sort of plate on the bottom to do to create the torsional rigidity.
Yeah.
Yeah, just to add to that, I would say that, yes, like some sort of plate cooling would offer protection from the outside, but it would impede protection from the inside. Like if something happens to the cell and you have something in like intimate contact with the bottom of the cell, then where does the hot gases and debris, because these things, once one goes into thermal runaway, it's not only hot gases, there's debris coming out of it. And then it would bounce right on this cooling plate and would basically be ejected sideways. And what's sideways would be like adjacent cells. So this is where I'm thinking that that's why they're going ribbon instead of plate cooling. But we will have like more episodes as we learn more about these systems and figure them out. I'm pretty sure Jordan is up to coming back and like nerd out with us and like investigate this. And I'm pretty sure he's going to be doing videos. So subscribe to his channel. I think you guys already know who he is on YouTube and on Twitter. Like go follow him, go subscribe him. Probably lots of good data coming forth. This is mostly like first impressions.
Yeah, gotcha. And all the typical venting comes out the top, the microscopic pores and the diaphragm we were talking about, that's placed on top, correct?
Well, I don't think the 4680 has that. It doesn't have that. Go ahead.
Well, let's be clear on what, just make sure we read it at the top and the bottom. Because I think with the 4680, there's that copper plug at the top. I think that's going to blow out and it's going to eject downwards rather than upwards into the passenger compartment.
Gotcha.
Does that make sense? Yeah.
Okay, so let's take the next caller. You're up, Moore. I'm not seeing your name fully.
Yeah,
sorry.
yeah.
Morehouse, go ahead.
You can hear me? All right, so to follow me,
Yep.
can you pull up two images, the Berlin poster and Alex, your pinned tweet, right? So in the Berlin poster, it appears that plate, that cover, is actually upside down, right? If you compare the geometry to your pinned tweet, it looks reversed, like it's flipped 180. You see what I'm talking about here?
Yeah, I think I do. Again, like
And
go
so
ahead.
that plate, if you stick it inside the circumference of the can will be sort of crimped over the lip, like you would say a soda can. That's kind of what I see here. And on the bottom left of that Brandenburg poster, it shows a little rivet, and that perfectly matches the rivet in your pinned tweet center, and that would perfectly go through that copper plate, if you will, and that sort of attaches all those three pieces together, like two pieces, if you will. But it looks to me in that Berlin image on that poster that top metal plate is flipped.
Yeah, I see what you mean, and it's the first time I've noticed it, whether it's flipped or not. But yes, it seemed that the bump.
If you flip that upside down, the geometry matches perfectly with the image from the B-roll from your pinned tweet.
Yeah,
And
I
then
think you're right.
And then the can
And of course,
circumference will be crimped over that inwards like a soda can.
yes, and this is the thing. Like the only difference, like I'm saying, is like it's on the border, because one would be like pre-crimp, and the one in my B-roll would be like already crimped on. So you can't focus on the edge because the edge will change. Correct. But if you focus on the center, yes, there is something Correct. There where like the center bump on the B-roll is pointing outside, and the other one is pointing inside. So yeah,
correct. And that
good catch.
That copper current collector appears to match the inside of that plate geometry as well. So I think that center rivet, as you explained earlier, is sort of there to hold those pieces together. And those 6 tabs are sort of like that spring cushion, if you will. But anyway, that's what I see.
Yeah, good catch. Yeah, I'm going to look into that. But I think you may have found something interesting here, that the lid is actually like flipped opposite to
I think they try to throw people off with that image. But that's what I see. Anyway, that's all I have.
Okay, but that's good. Thanks a lot. Going next, Ricky.
Hey guys.
How you doing?
I was looking at Jordan's tweet chain here, and down in the banners. So the idea is that this battery is going to be structural, correct?
You mean the cells are going to be used in a structural pack?
Yeah.
Yes, of course.
All right. So that last one where it has all the pieces where it's making the connection on top. So it's got to carry electric current. It's got to cool, and somewhere in there they got to put some kind of adhesive, right? I mean, is there some point where like adhesive would be a blocker? Because I don't know a lot about adhesives in this point. I'm carrying electric current, but where is the surface area that you're actually putting something to make this structural with an adhesive foam?
Well, it's a good question, but you got to know that adhesives comes in all sorts. So you have those who are electrically conductive, those who are electrically insulating. You have adhesives which are thermally conducting, which are thermally isolating, and you have all these combinations. They exist. My best guess, maybe Jordan, you want to feel this one. Like, how do you think they're going to make? Because we see the pack level current collectors, which are basically like welded. But how do you connect? And I think we've had this conversation before informally in private. How do you transfer shear through the can wall if you're not physically connected to the can wall?
Yeah, my best guess was on the video that I made that they sandwich everything in here as tightly as possible, and then they inject it. And that was the nature of our debate was, well, can you still do shear transfer if you do it like that? I don't know if we arrived at an answer.
Actually, like like actually I was of the opposite
Uh,
opinion,
s-
but drilling down more and more, my thinking started to move towards
Yeah.
Jordan. It's like, yes, if you want like maximum shear transfer, you need actual both sandwich plates to be like physically connected. This is like for the top maximum, but maybe maximum is not what's needed. Maybe just a certain amount of shear transfer is more than enough for what they need to do, and you don't need to over engineer it because it's not necessary. And you can hold on. I just want to complement that with
And how much?
if you look at the Giga Berlin structural pack, you can see the cells and the
yeah.
cooling ribbons. But if you look at the front of it, you'll see that they put like some mock cells and some foam. And I think that's how the whole structure, how the whole pack becomes structural, because it binds the cells with the plates, top and bottom, and it's like it provides. This is how the shear is transferred. So it goes from the bottom plate through a bit of foam, through the cell wall cans, through a bit of foam, through the top plate, and that's more than enough for what they need. And that foam is probably not the same brittle foam that we've seen people when Sandy Monroe takes apart a pack. It breaks in his hands. It might be something that's much more rigid and like sticky, that it can actually like transfer shear.
Yeah, that makes sense to me with that last picture where you see the pieces on top and they have holes over where the empty part between the cells would be. It would literally like have a binding agent coming up through that and then back down.
Yeah, everything is like enveloped in this structural foam that
Gotcha.
sticks to
Okay.
everything that it touches. And basically then you have a big sandwich. It's like I said, it's not as good as if like a pure honeycomb. If you've ever looked at like how they do carbon fiber or things like that, you'll see that they use a honeycomb and the plates are binded like with the minimum amount of glue to the top and bottom of the honeycomb section. And that's probably the maximum strength you can get. But you don't need maybe all that strength.
No, no, thanks for that because I was trying to envision that. It's like, man, there's so much going on here. And it almost made me wonder if that's why they were going with the ribbon cooling. Um, just because the top and bottom of those batteries are going they're carrying the current. They're gonna, yeah, there's just a lot going on there, man.
Yeah, that foam is probably a fire retardant. It's also probably well, more than probably, it has to be electrically insulating, and it's probably has very good mechanical properties. It's a combination of those three things that would make this pack structural and be able to flood everything that's in there without causing any problems, but actually solving some. All right.
And I think Ricky did a really good job of summarizing the problem that we're trying to tackle here. You have all these different requirements that this pack has to be able to achieve. How in the hell did they get all this to work in symphony? Because each thing is connected to every other thing, and it's a complex system. You touch one thing, and it has an impact on the thermal regulation, the conductivity, and the structural aspects of the battery pack. So it's a difficult problem to solve, and it's going to take us a while to unpack what exactly that they've done here. So I would add one more thing. I think a lot of this, the shear transfer we're talking about, I think a lot of it depends on how rigid that epoxy foam is. I'm assuming that it's not electrically conductive, but if there's no direct contact between the battery cells and the sheets on the top and the bottom, then that epoxy foam must be super rigid, and then the battery cells act as kind of like rebar does in concrete, just providing a bit more reinforcement throughout the length.
I wonder if anybody at Giga Berlin
You know,
was able to approach that mock-up and poke the foam to see how rigid it was. I would have tried.
that would have been awesome. I mean, it makes you wonder because everything else that they've tackled, I mean, from the bottom up, material science, like the way they changed the chemistry on the magnets and the motor. I mean, it makes you wonder if they've come up with something that could be rigid and just do the things that we're thinking it would do. All right, yeah. Thanks,
Thanks a
guys.
lot. Taking the next question, next caller, Scott, you're up. Scott, can you unmute? Yes, speak. Scott, going once, going twice. Okay, I think we're going to move to Landon. Landon, you're up.
Hi, thank you for having me up. Just want to say briefly, I don't have any education or experience in these fields, and the men and the women in this room and on the stage have done an excellent job here and elsewhere at helping me understand these concepts. So thank you personally for me and anybody else in my level of experience. So my question is, I'm wondering if now or in the future we'd care to speculate on what this technology does for potential pack sizes in the vehicles that 4680s are likely to go in. For example, we're thinking semi, Cybertruck, and Model Y. If we look at the current pack sizes in the vehicles that exist now, like a Model Y, my 2020, I believe, came with a 77 as a pack size, and was then moved up by Tesla, not my vehicle, but the production Model Ys after mine, to an 82. So do you think that Tesla would keep a similar pack size and have a more efficient vehicle, or would they move to a smaller pack size again for similar range? Thank you.
Yeah,
Sawyer, Jordan, you're
I'll
up.
take a step. I think I would like to see them keep the pack size the same and increase the range. I'm not in the camp that they would drastically increase the size of the pack, but I also don't want to see them decrease the size. I think with the additional efficiencies they can get with these new technologies, keep the pack size the same and increase the mileage. And a lot of the reason I say that is because that's what they've done in the past. They keep the pack size the same, and then they give you more range through efficiency improvements. But I'm interested to hear.
Yeah. Yeah, I was just going to say, the same size pack, if you're able to reduce the weight by removing structural elements and that kind of thing, can actually give you more range. So there will be an improvement just in that. And then I also know that the semi, I think, is going to be around a megawatt hour.
Sawyer, what are your thoughts on this?
Yeah, I'll say my thoughts have sort of been developing. I used to think that they might put less cells in it, and that way they'd have more cells for more cars. But I would say in the last week, I've sort of been tilting more towards Jordan's opinion, where they'll sort of keep the pack similar size, and they'll increase the range. And I'm hoping I can sort of shed more light on why I think that. But yeah, I think they'll probably bump up the range.
Nice. A follow-up question, Landon?
Just perhaps if you could speak to what variables might be in play there to make that decision. What would you say are priorities for a new vehicle? Like, is it weight reduction? Is it saving the number of cells? Or is it the structural pack itself? Is the integrity important to have a certain number of cells in it, or any other factors I might not be thinking of?
Well, I think on some level, this is like you're mentioning a whole bunch of variables that basically add to the same thing. So if you can, like Omar said, like reduce weight because you're not employing so many like dead structural components, but actually active structural components, then you get, with the same size pack in kilowatt hours, you get more range. Same as with efficiency, what Jordan was mentioning, with motors getting more efficient and then being able to go further on less. All these things like are part of the same equation. And of course, the more batteries you add, even if it's structural, the more weight you're carrying around. I would say that I'm somewhere in the middle. I think Tesla will do actually both. We'll actually probably make the packs a bit smaller and still increase the range. They'll be the leader in efficiency and range, but they won't like jump like 3 steps ahead of what's available on the market just for the sake of doing it, because this also affects the margins and how many vehicles you can make. So I think they'll continue to be the leader in range, both like in battery and efficiency, but they're not going to give you everything that they could give you by filling the same volume that's, let's say, in a Model Y today with 2170s, by filling all that with 4680s, because there's no point in doing it. Like, there's no point in offering like a 600-700 mile range car today if the market is not there and charge the same thing to be competitive on sale price. So I think they'll always incrementally increase. And for the safety, I don't think it matters at all. Like, even if you think about safety and agility, like Elon mentioned, like the closer you put the cells to the center of the car, you get like 2 benefits. First, it's more maneuverable. But secondly, let's say you get a side impact for whatever reasons, the batteries are really inside the car so far that they're not in danger of being impacted. So just filling it for the sake of filling it, I don't think they'll do that, but I think they will remain the leaders in range and efficiency.
Well, if you go back to what they did with the Plaid Model S, who was it? Motor Trend, something like that. They said the battery pack size was a little bit smaller than it was before, something like 100 kilowatt hours. But they didn't say where they got that information. But I don't know if you saw online today on YouTube, but there's a guy that claims to have a Plaid battery pack, and he listed the number of battery cells. And when I calculated that, it came to about 90 kilowatt hours. So at most 95. So it looks like Tesla, if that video is accurate, then they are able to remove 5 to 10 kilowatt hours out of the battery pack and still slightly increase the range. So you might that could happen as well. But I do think the battery pack will not get larger because they're going to try to stretch these cells as far as they can.
And to that video, there's a lot to unpack in that video. The quality of the video is not great. The guy's running around, I think, with his phone. But yeah, there's a lot of new interesting tech and developments that they put into the Plaid pack. For example, like the cooling, the inlets and the outlets are both on the same side, which is, I think, pretty unusual. And all sorts of stuff. But this is maybe for another episode.
Thanks. I hope the rest of your week's good.
Thanks a lot. You too, Landon. Okay, we're going to give Scott another chance. Next caller. You're up, Scott.
Hey, can you hear me now?
Yes, we can hear you.
Sorry about that. So my comment was on for the thermals on the cell can. If the thermals are mostly going through the top and the bottom, then do you have expansion of the can radially outward and inward? Versus if the thermals are going to the sides, then the expansion would be up and down, taller and shorter. So I don't know if that would affect how they design it.
What do you think, Jordan?
Thanks.
Have you considered like where the initial heat is dumped? If it's dumped like on the bottom versus the sides, which would be better for the overall life of the battery?
I think it's better for the life of the battery, just in terms of, I don't think it's going to have to do with expansion and contraction, but that's me taking a guess, because all materials have, at least as I understand it, different rates of expansion dependent on how much temperature that they're exposed to. I think you and I calculated it for that new gigacasting. It was something like it's just a few millimeters for something that was a couple meters long. So it's just infinitesimally small amount of expansion. And we're talking a wide temperature range of something like 50 degrees Celsius. So I don't think that'll be a factor here, but I do think that the way that you pull the heat out of the battery cell And the uniformity that you're able to do that will affect battery life.
That makes sense to me. The other
So
comment I'd
that's
make on the battery pack sizes is as long as they're cell constrained, they will try to not increase battery pack sizes. Thanks.
Thanks a lot, Scott. So we've been going at it for almost an hour and a half, and we don't have any more callers. So I think we're going to end it here. What do you guys think?
Yeah, no, absolutely. I think it was a great call and or podcast, I should say, and it was sort of cool to be a fly on the wall for the conversation you guys had.
Well, I want to thank Jordan. Like this, thank you for coming on and nerding out with us. Hope we can do it again. We have so much to cover all the way up to the structural pack and all that. So, yeah, hope you'll join us again.
Yeah, I enjoyed it, and I hope everybody else enjoyed it as well. We're getting into quite a bit of depth there. So if people got something out of it, then great, because I often have conversations like this with battery researchers, etc., but I try to boil things down when I put it on my channel. But I do think there's a lot of value watching two people work through a problem together. So
absolutely, I always enjoy it. It's not our first time doing it, but I think it's our first time doing it in public. So I think we should do it more like every time we have a little breakthrough, maybe do our first impressions, nerd out. And I'm hoping you will do like a series or at least a video once you have like enough information to do another like deep dive on the cell and the battery pack. Really enjoy your content. Again, I want to tell everybody here listening, please give a follow here on Colin to Jordan and also his YouTube channel and Twitter. It's always very good information.
Thank you so much, Jordan. That was awesome.
All right. So with that, we're going to close this room. Thank you all for being here. And the episode will be published on Colin shortly and probably tomorrow on YouTube for those Android folks who can't have access to it just yet. So make sure if you see people crying about it, that they'll be able to access it on YouTube until like Colin makes it available to Android users. Well, thank you all and have a nice evening.
Thank you.
Later, man. Cheers.